All right, guys, let's go ahead and get started. All right, I think we left off in the middle of a problem. Y'all refresh me, because I don't remember what it was. I know it had something to do with acetals. Was acetone part of it? What was I reacting acetone with? What's that? No, well, yeah, I had an OH. As an it should have been an alcohol, like two equivalents of some sort of alcohol, but I can't remember what it was. Was it ethanol? Yeah. Ethanol? Okay. Just wanted to make sure. And then we had some sulfuric acid. So I think we did phase one of this, right? So you remember each stage of this basically involves action of the acid, right? So just to sort of catch us up, oxygen grabs an H. And since this is actually an equilibrium reaction, it's reversible, so I'm going to make sure to draw equilibrium arrows. So gave us the positive O, which made this carbon more reactive. And the alcohol can attack. And we said HSO4 minus, which was left over from the first step. You come back, grab that H, and give us our hemiacetal. So this was the halfway point. Okay, so that's where we got the other day. All right, so remember, each phase of this begins with the action of the acid and ends with the reformation of the acid. All right. So when we start phase two with the hemiacetal, that means this H2SO4 is going to do something again to sort of start things up. All right. What do y'all think might happen here? What do you think the sulfuric acid can do? Well, acids like to donate protons, right? So where do you think is a good spot that can accept that proton? Yeah, you got an OH over here. That's what happens. This OH will grab a proton. Really should have left myself more room. Creative here. All right. Gives you that. All right, so now we have water over here. What do we know about water? It's a good leaving group. So it's going to leave and that's going to leave a carbocation right there, full positive charge. All right. probably a good place to be attacked by something. What do you think might be able to attack that positive charge? Well, what do we have left? Boom. Yeah. We have two equivalents of the ethanol, right? And we're going to use both of them. So that alcohol can come in and attach itself. Let's see. And it gives you that. So now that gets our second alcohol group attached. And that's the basis for formation of our acetals, right? We got to get two alcohol groups attached. We've done that. And there's just one more step in the mechanism. What do we have to do? Very good. Yep, HSO4 minus. Which I'll draw over here. HSO4 minus left over from the first step of the second phase. Come in, grab that H, and don't worry, I will circle the final answer. I know there's a bunch of crap on this board here. And that gives us our final product. So this mechanism is a little bit more involved, right? It's a little bit longer. It's got some more steps as opposed to some of the other ones that we've done. However, again, there are certain patterns that you can recognize here. And I think sort of dividing it up into phases kind of helps things. If you're ever doing this and you look at these milestones, you can look for certain things, right? So at the end of phase one, you can double check to make sure that number one, you've made a hemiacetal, and number two, you've reformed your sulfuric acid. Same thing for the end, except instead of a hemiacetal, a full acetal. If you can't reform the acid catalyst, then you might have gone a little awry somewhere. Okay? Does that make sense? Are there any questions so far? So yeah, this is definitely a pretty important mechanism. No, although if you're just kind of doing predict the product type of stuff, it's pretty easy, I think, to figure out what can go there where without using a mechanism. Oh, let's see. Let's just do this. Say we have that aldehyde. And let's use isopropyl alcohol. And just for fun, we'll use para-toluene sulfonic acid. All right. Now, the mechanism of this is exactly the same as we did for the last one. Right? So I'll let you guys go through that on your own. But you can predict the product here pretty easily. All right. Just remember, the carbonyl carbon is where all the reaction is going to happen, right? That's going to be the place that's going to be getting attacked. What do you think is going to end up on that carbon? I'm just going to draw a partial there. Well, ask yourself, what does an acetal have? What does an acetal have that an aldehyde doesn't? Look it up if you have to. What does an acetal have? That maldehyde doesn't. I know there's no genetics test today, so you're not sitting there looking for your genetics names. Y'all should be able to answer this. You guys are stubborn. I am too. What do you say now an acetyl has? Got a carbon that has what on it? What's that? The OR groups. That's going to be the really important thing here, right? So, you know you're going to have two OR groups present in your acetyl that were not there originally. Where do the OR groups come from? Well, they come from there, right? So, if I'm trying to predict the product of this, let me just stick one of these on there. Let me just stick another one on there. And viola, we have our acetal, right? So just look at the aldehyde or ketone that you have. Recognize that it's going to form an acetal. And then you just put two OR groups, and that comes from your alcohol. Right, that's sort of an easy, short way that you can use to predict the products of one of these reactions. Although, like I said, you are going to need to know the mechanism. We're going to go through another mechanism here in just a minute. So, does that make sense? Are there any questions so far? All right. So here's something that's pretty fun, I think. Anyway, you can do this with cyclic ketones. Right? We can make an acetal out of that. That is a hexagon, even though it's kind of a poor looking one. So you can do this. I mean, you can make a cyclic ketone into any type of acetal, right? So we could put two equivalents of ethanol or isopropyl alcohol or whatever. But we're going to do something a little different. We're going to add one equivalent of that. And the purpose for this is we're going to be trying to make a cyclic acetal. The previous ones we looked at have been acyclic, right? The acetal itself was not a cyclic species. But now we can actually make a cyclic acetal. And to do that, it basically works the same way, but there's just one little tweak, all right? What's the obvious difference between this one and one of the previous examples we looked at? We have a diol, right? We don't have something like ethanol where you have just one OH. We have two OHs. So we use a diol. How many equivalents of this do we use? It's just one. Yeah. The whole point is you want two reactive alcohol groups, right? You can either get that from two compounds that have one alcohol group, or you can use one diol. And that's what we're going to do here to make a cyclic acetal. As for the mechanism, it's no different than what we did before. So, guide me through it. What happens first? Phase one. What happens in the beginning of phase one? TSOH is absolutely going to protonate the ketone. Yep. Action of the acid. It's going to make this oxygen positive, which it hates. and in turn makes that carbonyl carbon more reactive. What's going to attack the carbonyl carbon? The alcohol. All right. So in this case, just like before, we can see attack of the OH. It's going to carry all the rest of that molecule with it. So you get that, right? Same thing as last time. Alcohol group is now attached to your former carbonyl carbon. The only difference is now the rest of it just happens to have another OH. All right. End of phase one happens when your acid reforms. So TSO minus will take that hydrogen. And that gives you your hemiacetal. And that's the end of the first phase. Oh, I guess I should draw the TSOH that we just reformed. That'll be important. Yeah. So far, so good. All right. So beginning of the second phase, what's going to happen? TSOH is going to protonate your OH. Yep, just like last time. Okay. Now what? Water's good leaving group. So it's going to leave. That leaves the carbocation. Now is where things are going to look a little different compared to the last examples that we've seen. All right, what happened last time at this point? Once you got to the carbocation. That other alcohol would come in, right? The second equivalent. Well, we don't have a second equivalent of that molecule there, right? But do we have another reactive OH? Yeah, we do. It just happens to be stuck to the rest of the molecule here. So what you get is what we call an intramolecular reaction. That's where part of the molecule reacts with itself. So this OH is going to loop around. It's not going to detach. It's going to just loop around and attack that carbon. And it makes another ring. And the last step is, again, TSO minus will be protonated. This is challenging. You know that I restricted my board space because of Zoom. And that gives you your product. And if you look at this, right, you got this carbon, it's got two R groups, and even though it looks a little funny, it's got two OR groups, right? Each half of this ring is basically an OR group. So yeah, it does classify as an acetal, specifically a cyclic acetal. Kind of looks like a little, I don't know, cartoon bug or something. Cartoon little robot or something. I'm not sure. Yeah, that's how you make a cyclic acetal. And you can do this with a straight chain ketone or aldehyde too. It doesn't have to be cyclohexanone. As long as you use a diol, then yeah, you'll get a cyclic species. Okay. Does that make sense? Are there any questions so far? All right. All right. Here's something you're going to like. You notice these reactions were reversible. That's why I drew the equilibrium arrows. You can go backwards. You can take an acetal and you can hydrolyze it to form its initial respective ketone or aldehyde and alcohol components. So guess what? All that stuff we've been doing, we're going to do it again, but reverse order. Woo! Yeah. See a couple of you nodding? Yeah, that's the spirit. All right. Let's take a look here. So let's say we started off with an acetal. All right. Here's how you set it up. You're going to add water. And again, you're going to have the presence of some sort of strong acid, either TSOH or H2SO4. I'll just use sulfuric in this case. All right. Here's something very, very important here. You add water in excess. You want to drown this reaction. You want to use a lot of water. That'll be important later on. Okay. Much like last time, even though this is going backwards, we can still divide this up in phases. Each phase will begin and end, but we'll begin with the action of the acid and we'll end with the reformation of the acid, just like last time. Okay. So if we're looking at this, again, the first thing that's going to happen is that sulfuric acid is going to protonate something, right? Well, what do you think it's going to protonate? One of the oxygens. Yeah, we'll just pick one. That one will work. Okay. And we get that. All right. Now, we've talked about the fact that in the past that water is a really good leaving group, right? Well, one thing about alcohols is that they're very, very similar in a lot of their properties to water, right? So you may notice that this right here, that's an alcohol. That's CH3OH. Water is a good leaving group. Alcohols are also really good leaving groups. So that alcohol group is going to leave. And that's going to leave you with carbocation. And a molecule of CH3OH that you just gave up. I'm going to put a rectangle around that because that is one of your products. That's one of your organic products, right? We should end up with two equivalents of methanol eventually. That's one of them. Then you got this, all right? You've got a full-on carbocation there. What do you think that's going to mean for the next step? Any guesses as to what's going to happen to that carbocation? It's got a full positive. What haven't we used yet? The H2O, yeah, water. Water is a really weak nucleophile, but since this is a full positive, it can attack. So water will come in and attach itself. Let's see, I'm gonna go this way. Maybe they'll leave me more room. Gotta make more efficient use of the board space. So water can attack. And we end phase one by deprotonating that to get this. And if you look closely, you'll recognize that that is a hemiacetal, right? That carbon has one OR and one OH, hemiacetal. So you get the same basic half-life. You also reform sulfuric acid. Okay. Halfway home. Y'all hanging with me? Does that make sense? Any questions so far? All right. So now we have to start phase two. That means the sulfuric acid has to do something. What do you think it's going to do? Which one? Not the one with the OH, the OR group, right? Yes, that is very important. It does not attack the OH. And here's a good question. People ask, well, why doesn't it? We've seen, the acid protonate OH in lots of other cases. Why not protonate the OH in this case? Well, what would that make? It would make water, right? And they say, well, water's a good leaving group, right? Well, then you're just going backwards for one thing. But also, we've put a very important factor into this reaction scheme that prevents this from happening, all right? We have an excess of water already, right? So that means there's already lots of water in here. There's a certain principle that you guys learned about, not only in Gen Chem, but probably all through high school too, that dealt with equilibrium. All remember the name of it? Begins with an L. Think French person. I think French. Kind of the name sounds French anyway. You look like you want to say something. Say it. You are absolutely correct. Le Chatelier's principle, right? You guys remember Le Chatelier's principle? Or at least talking about it? No? Okay, well, let me refresh you. Le Chatelier's principle states that when you have an equilibrium, it can favor one side or the other. It can be shifted one way or the other, right? But if you already, one of the parts of it is that if you already have excess species in there, you're not going to be able to make more of them, right? So our system has excess water in it already. Does it want any more? No. It wants to get rid of water. So the system is very resistant to allowing the formation of more water. That's why the sulfuric acid goes after that guy instead of your OH. If we did not have an excess of water, then we'd have a problem. Because then, yeah, this would freely deprotonate and we'd be just going backwards. So that's why you always want to use an excess of water when hydrolyzing an acetal. All right, so you end up with that. Just like we said before, That's an alcohol. That's a good leaving group, so it's going to leave. So you end up with carbocation. And here is your second equivalent of methanol, which is again part of a product. So we've reformed the two alcohol equivalents of our product. Now we just have to get back to the aldehyde or ketone. All right. If you look at this carbocation, you can actually draw a resonance structure where those electrons are swooped down. So I'm going to draw my resonance arrows. And you see this is now starting to take the shape of a ketone, right? Resonance form, we have our carbon-oxygen double bond. There's only one more step here. What is it? HSO4 minus grabs your proton. Very good. And boom. That gives us our ketone. And then you also reform your acid. Whew. A lot of good mechanism stuff today. So, products of this, one ketone, two equivalents of methanol. Okay. Are there any questions about how we got from the acetal to the products? Does that make sense? Now that we know how to do both formation of acetals and hydrolysis of acetals, that means we can do some pretty interesting things here. One of them, let me get this erased. One of those things that we can do is we can use acetals as protecting groups. I don't think I've talked about protecting groups before, have I? Like, probably. At some point. When in and out. No. Basically, what a protecting group is use a protecting group when you have a situation where, let's say you have a molecule, and maybe it has a couple of functional groups on there, a couple of reactive functional groups, and you want to do something with one of them. However, there's a problem. The problem is whatever you want to do at one functional group is sort of interfered with by another one, right? So what you can use a protecting group for is to sort of tie up one functional group, carry out your desired reaction, and then deprotect it to reform the original group. Right? Let me give you an example. Let's say we wanted to do, I don't know, let's see. Let's say we had something like this. All right, so that's a compound that's got both a ketone group and an acid chloride. Okay, here's what we want to do. We want to react it with lithium aluminum hydride and water, and we want to react it specifically at the acid chloride group. And we want to try to make that compound. That's our target. What's the problem here, though? Lithium aluminum hydride is a strong hydride source, right? Obviously, it can react with an acid chloride. Can it react with a ketone? Guys, looks like so over this. Think back, hang in there. We only got what, 3 more weeks or so, something like that, 2 or 3 more weeks. I'll answer for you. Yes. This can react not only with acid chloride, but it can also react with a ketone as well. That's a problem. All right, so wouldn't it be great if we could sort of tie up that ketone for a while, do our thing with the acid chloride, and then reform it? The answer is yes, you can. Right? That's fantastic. Here's what we can do. All right, first step is to protect your ketone. All right? So basically, we're going to temporarily react that ketone to put it in a form where it's not going to react with this. All right? One thing that we learned that we can do is we can make cyclic acetals. So here's how I would approach this. I would try to make this compound, right? And I can do that with a diol and a strong acid. And that can turn that into an acetal. Here's the great thing. Acetal, not reactive with this stuff, right? So that leads us into step 2. That's where you carry out your desired reaction. So now I'm free to work with the acid chloride however I want to. So I can put in my hydride source. And I can make my OH group. Okay. So far, so good. Any questions? Now, I've only got one problem though. I don't want that acetal group there anymore. I need to have the molecule in its original form at that point in the molecule. We need a ketone group there. Is there any way that we can go take this acetal and reform our ketone? Marissa, I see you nodding. How would you do that? So funny, I say your name and your eyes get, ooh.
We'll just be the
Yeah, take that acetal and hydrolyze it, right? That's one of the beauties of acetal formation, is reversible. So, step 3 of the process is to deprotect. And in this case, we can do that using an excess of water and an acid catalyst. And voila, that gives us our final product. So it's a pretty cool little application of acetal chemistry. The fact that you can tie up one ketone or aldehyde group, protect it, and then do something else with some other part of the molecule. Are there any questions about how we did that? By the way, this is not the only type of protecting group that you can have. I can make a whole class on protecting groups. This is just one example. In fact, there was an example in chapter 20 that I forgot to go over with you. But honestly, it's not really that important for you guys, so I'm not too concerned about it. This is a really cool application. All right. one more thing related to acetyl chemistry I want to talk about. And this is something that actually is going to be pretty relatable for you guys once you, if and when you take biochemistry. How many of y'all are going to take biochem? Ooh, yes, good. Preview of biochem, sort of. All right, let's talk a little bit about cyclic hemiacetals. So you recognize the term hemiacetal. Hemi is half, so basically half an acetal here. But specifically, we want this half of an acetal to be in a cyclic form. Okay? All right, so to make a cyclic hemiacetal, basically, you need a chain. Let's see. I might erase this depending on sort of freewheeling off the top of my head. Oh, this will work. Let's say you had something like that. All right. Now, you know, when we make an acetal, we need an aldehyde or ketone, and we need 2 equivalents of alcohol, right? To make a hemiacetal, what do you think the only difference is? To make an acetal, you need an aldehyde or ketone plus 2 equivalents of alcohol. To make a hemi, or half acetal, what's that? 1 equivalent of alcohol. Yeah, very good. And to make a cyclic hemiacetal, you want that 1 equivalent of alcohol to be on the same chain as your aldehyde or ketone. And that's what I have here. And it works the same way. In the lab, you can do this with a strong acid. The mechanism is going to be exactly the same as you've seen before, right? You're going to have protonation of your carbonyl oxygen. Right, to give you that. Now we need a reactive alcohol group to attack the carbonyl carbon. Well, guess what? We got one. It just so happens to be on the same molecule. So this is another intramolecular reaction. And that's how we form the ring, right? Because this loops back upon itself and attacks the other end. So this is going to be a 1, 2, 3, 4, 5, 6 membered ring. And one of those members is this oxygen right over here. Okay, so once you get that attack, it transformed from an acyclic chain to a cyclic molecule. Last step, it's just simply deprotonation. And boom, you've got your cyclic hemiacetal. All right, hemiacetal because this carbon has 1 OH and 1 OR. So that's how you make them in the lab, right? One application that you'll see in biochemistry is when you get to carbohydrates, sugars. You guys have probably heard of like glucose before, galactose, all those oses, right? Well, one thing that you're going to see with simple sugars like glucose is that they're kind of funny. They can exist in a straight chain, They can also exist in a cyclic chain. Glucose, for instance, has an aldehyde group and several OHs. So what happens is you eventually sort of reach an equilibrium where some of it is existing in a cyclic form, like at the very beginning here. Some of it is existing in the ring form. It's also catalyzed by an enzyme, not by an acid in that case. Believe it or not, you don't have sulfuric acid running through your veins to catalyze the formation of cyclic sugars. Kind of cool to think about, but not so much. But yeah, but this is basically the same way that it happens in biochem. So kind of a neat little application. Any questions about acetals? All right, there's one more reaction set I want to go over. It's actually a quick one. It's one I kind of accidentally skipped before we got to the acetals, but it is worth mentioning. That's called hydrate formation. And hydrate basically is just another term for geminal diols or gem diols. And if y'all remember, a gem diol is basically a carbon that's got two OH groups on it. And one way that you can use to make these is through aldehydes and ketones. Super simple, actually. There's two different ways you can do this. First way is to use water in the presence of basic medium. So an OH, H2O and OH, H2O and OH minus. Let's try to guess the mechanism. It's really easy, really short. Carbonyl carbon, blah, blah, blah. Carbon gets attacked. Same old story that you've seen before. What do you think can attack the carbonyl carbon here? Yeah, you got that OH minus, really powerful, strong nucleophile. That attacks that. Electrons go up to oxygen. Gives you that. What do you think the last step is? H2O will protonate the O minus. And that's it. Boom. It's a lot simpler than that acetal mechanism. Right. So that's one way that you can use to make gem diols or hydrates. The other one is really similar, except for the fact that instead of being base catalyzed, it's acid catalyzed. So we draw a little line over here, keep it separated. So this one's slightly different because, you know, in this case, you had a really powerful nucleophile. So this was able to attack, you know, right away. Here, you don't have a powerful nucleophile. Your nucleophile is going to be water, which is a puny little weak one. So what that means is we got to make this more reactive. And to do that, we do the same thing that we did in the acetal reaction. We protonate that oxygen. Give you that. Now, this carbon's reactive enough for water to come in. and then another water can come along and deprotonate that guy. Sorry, I kind of fast forwarded to this one since we're almost out of time. But it gets you to the same place. So take your aldehyde or ketone and either use acidic or basic media in the presence of water. Whew. Any questions? Hey, guess what? That's the end of chapter 21. Woo. All right. Hey, we need to take a third exam. Ooh. Yeah, I never know. Check with that. Yeah, we got to do it. So let's plan for next week. We could do it this week. We are ready for it. We finished all 3 chapters. No? Next week? All right. Your choice. It will cover chapter 18, chapter 20, and chapter 21. This one's kind of heavy duty. There's a lot of stuff on it. So be very proactive. I don't know if you've noticed or not, I do actually have sapling problems up for this chapter already. So go ahead and be working those. I will also send out some optional practice problems for the PDF version. All right. Have a good one. All right, Riley. Come on down for a second. Yes. Yeah. I sent him a tweet, so let's plan to meet up in the office back at 9:15. All right. I have a couple of quick meetings to go there. Okay. All right. Were there any other softball girls that needed to do this?
Tori and Nikki.
What's that?
Tori and Nikki.
Tori and Nikki, come on down.
Oh, you look nuts. Huh? You look nuts.
Well, we're trying to work out a. Nobody's in trouble. Gosh.
Yeah.
All right. So you sent me the thing about the virtual lab.
Yeah.
I do have one, but in a nutshell, it sucks. I think it would be better for you to actually go through this. So, is there any possible times where you guys could come in and do this together, or even where you could tag team, where like somebody does part of it? Do y'all have any commonalities in your schedules?
Yeah, it depends on when Coach sends out the email when we have to do
Oh.
stuff.
Yeah,
Okay.
we just have games the next 2 days.
Yeah, games the next 2 days?
Yeah.
Okay. Y'all have like you play games are there certain days of the weeks where you have games and like certain days that you always have off, or is it just random?
It's random. It's random.
Okay.
Sorry.
Okay.
Stuff gets moved around all the time.
All right, let me think for a second. All right. What I'll do then is I'll let you guys do the virtual lab. But what I'll probably do is, at the very least, I want you guys to analyze the reactions and do yields and stuff like that, and come up with analyses based on melting points. So what I might have you do is go through the virtual lab, get that data, and then also have somebody else give their data to you to write a more involved lab report. Does that sound doable?
Mm-hmm.
Okay, sounds good.
Thank you.
Thank you.
Right. Grace, want us to go out to the hall?
You should have it. One. And they and there's one air to get from space restaurant, right? Yeah. And they wanted to come as a hit, right? And I'll take you to Italy. And so my coach right now, she's like, I don't have to change because of that. Ridiculous. It's unfair to do that. It's clearly. I'm just gonna take a few pictures of the one. I think I'm missing this one. And this one. I'll be right back. Are you going anywhere? No. Yeah. No. Okay.
Is that still recording? Is it? Because I definitely just walked straight past it. Okay. How are you doing? Tired. It's a bad day today. I don't really have a reason. Just yeah, like freaking snow. Like what is that?
They're real busy.
It's fine. It's not like it's April or anything. I hope your day gets better.
Yeah, and I don't know offhand.